Hello everyone, I'm going to be presenting our project camera trajectory tracker today, which we do using monocular visual odometry. Basically, the motivation for this is to generate a line map of indoor floors by capturing a video of the whole floor using a single camera and using that to generate a trajectory of the path that was walked. Such a trajectory can further be applied for indoor navigation. It can be used to find paths and exact room location inside buildings, and it'll be especially effective for malls, college campuses, and other areas. There are also a lot of existing implementations of this sort, but most of them deal with outdoor environments rather than indoor, and therefore we had this interest to create a indoor tracking navigation system. Basically, our approach is following the current state of the art, which is OrbSlam2 algorithm. We're building upon that, but OrbSlam2 provides a localization mode, which localizes the camera in the map and outputs a trajectory of the motion of the camera. This is most relevant to us, obviously, because we're trying to generate the trajectory of the camera in an indoor environment. Most of the implementations of OrbSlam2 have dealt with outdoor environments. OrbSlam2 has been tested out on a lot of data sets, but most importantly the KITTI dataset, which has support for testing monocular, stereo, and RGBD approaches, and it's the most efficient algorithm based on testing on that dataset. So our implementation has basically 5 parts. We take a stream of grayscale images, which are captured at different time intervals. We take the frame, perform feature detection using fast corner detector, and using those features, we feed those features to the KLT tracker, which then finds a corner to be finds every corner to be tracked and uses this local information to track that corner and find that corner in the next image. Then after we have the points between successive frames, we use a ransack algorithm to randomly sample 5 points from the set of points pairs, and on the basis of these points we create a matrix using the Nister's 5-point algorithm, and we use it to further estimate a rotation matrix and translation vector. So as you can see, we're presenting the implementation of this on the KITTI dataset. Now the KITTI dataset is a dataset that contains 11 sequences from a car driven around a residential area with accurate ground truth. It is a very challenging data set for monocular vision due to fast rotation, areas with a lot of foliage, which make more difficult data association and at a relatively high GAR speed. And as you can see on the right, it is correctly tracking the movement from the series of images that we get on the left, and it is correctly estimating the turns and rotations even at very high speeds and at high rotational angles. So after testing out our implementation for the KITTI dataset, we tried to test it out on natively generated videos. The first one we tried to do, we tried to take a video from a mobile phone at college library, and as you can see, even with a lot of open area and a lot of movement in frame, it is still tracking the rotation right now. As you can see on the right, it's turning now, and you can see that turn being mapped out on the right. And next we tested it out on an indoor hallway in an apartment building, and this is a very narrow hallway. And as you can see, as we start, it is accurately estimating the movement. As we turn, we will see a turn in the tracking on the right. As you can see, there's a lot of convolution on this part of the tracking, and we'll discuss why. It's because for the KITTI dataset we had a scale file, but for the natively generated dataset we did not have a scalable file, so we had to come up with the right values using trial and error, and therefore even with the implementation with these values, there are small errors with the trajectory. Thank you.